All right, so another real-world problem where we're talking about things that are changing with respect to time, and if we utilize our ability to work with expressions, equations that involve variables changing with respect to time, we can actually get relevant information about the problem computed. So here's the problem at hand. We've got an airplane flying overhead at a constant elevation of 4,000 feet. So let's try to visualize this. I gotta be honest, in these problems, coming up with a visualization of what is going on is almost always wonderfully helpful. And once you have the visualization, the problem is so much more doable than if you didn't take the time to draw out the particulars. So we've got an airplane flying overhead at a constant elevation of 4,000 feet. So you can imagine the airplane flying, and constant elevation of 4,000 feet means the airplane is 4,000 feet off of the ground. Okay, a man is viewing this airplane from a position that is 3,000 feet from the plane along the ground. So here is somebody who is viewing the airplane, and that person is 3,000 feet from the plane along the ground. Now, I didn't note, by the way, I have not drawn this to scale. The 3,000 feet looks longer than the 4,000 feet, but I've labeled things properly. We've got the man along the ground, we've got the plane 4,000 feet off the ground, so even though this picture may not be to scale, it's actually going to accurately capture the relevant information of interest, which is the man's 3,000 feet away along the ground, the plane's 4,000 feet up. Okay, now, if the plane is flying away from the man at a rate of 600 feet per second. Okay, so let's try to visualize this. So now the plane is moving, right? And the plane is moving at a rate of 600 feet per second. So here's the picture. You can imagine the plane zooming off at 600 feet per second. The question is, at what rate is the straight line distance between the man and the plane changing? So the plane is moving at 600 feet per second horizontally, but so that's going to affect this 3,000 feet measure exactly, right? So a second later, this 3,000 is going to be 3,600 because the plane's moving at 600 feet per second. But the question is not about how far the man is from the plane along the ground. The question is, at what rate is the straight line distance between the man and the plane changing? So that straight line distance is here. Let's use D for that straight line distance. I'll capital D to make it, because we're going to get little d's from derivatives. So I'm going to use a capital D to distinguish that. But here's the long story short is now we have a situation for, now we have a description for the situation. And what we're trying to do is find the rate at which this straight line distance is changing. So what we're trying to find is not what the distance is, because frankly, if you just want to know what this distance is, because the ground and the plane's altitude meet at 90-degree angles, you could find the D just using Pythagoras. The question is not what is the distance. The question is, at what rate is that distance changing with respect to time? So the question is all about the change in the distance with respect to time, the dd dt. Okay, so now, if we want to find what the change in the distance is with respect to time, that change in the capital D, we've got to come up with some way of getting all of the information that we have at play involved. So I tell you what, just for simplicity's sake, let's call this horizontal distance x. Let's call the vertical distance y. Now, with that in mind, we can really start to play ball, because you see this 600 feet per second, how fast the plane's moving is actually a rate of change. So you can see in the expression, this is with respect to time here, what is changing with respect to time? Well, as the plane moves horizontally, the x is changing with respect to time. So this 600 feet per second is dx dt. Once we establish this varying thing along the x-axis along the ground, the distance between the man and the plane along the ground, once we establish that varying thing as x, then you can describe the change in that in terms of a calculus notation. Note, by the way, The y is not changing. The plane was at a constant elevation, so whenever we talk about the change in the y is going to be 0. Okay, but now we've got to work all this information together, and it's like, okay, if we want to find out what dd over dt is, and we know what dx over dt and dy over dt is, the question is, can we come up with a relation between x and y and d? Because if we come up with a relation between x and y and d, we could use derivative on that relation to get things in terms of dx, dy, and dd. So, let's ask the question, is there a relation between x and y and d? Yes, right? X, y, and d are sides of a right triangle. And you know, when you're dealing with sides of a right triangle, Pythagorean theorem applies. So in this case, x squared plus y squared equals d squared. And this is cool and useful and relevant, frankly, but in order to address the question of dd over dt, we're going to need to take a derivative. So let's do just that. So first, take the derivative of the x. That x is a variable with respect to time, so we tack on our dx and then our dt in the denominator. The y squared has a derivative of 2y. We're going to tack on the dy and the subsequent dt, since this is a variable change with respect to time. And then we get 2d times dd dt. Okay, here is our expression now involving our dd, our dy, and our dx. Let's plug in what we know to try to figure out what we don't. We want to get dd over dt being the only thing in our expression which is not a number. So let's start plugging in. What is, okay, we got a 2, what is x? X is 3,000 feet. What is dx dt? That's how the horizontal measure is changing. The horizontal measure is changing at a rate of 600 feet per second. That's how fast the plane is zooming along. What about the y? Because we need y in order to get dd dt is the only thing left as a letter. We need to know what y is, but we know what y is because y was the height, and the height of the plane was 4,000. We also know what dy over dt is because actually dy over dt isn't changing. So dy over dt is 0, and in fact because of that, that whole expression is going to drop out because 2 times 4,000 times 0 is just 0. What about on the right hand side? We've got a 2 times a d times dd dt. Now dd dt we know is going to be left over. That's what we need to solve for. But then the thing is, okay, what is d? Because we don't have d yet, but if we just had d, we'd have every bit of information we need to solve for dd over dt. What is d? Well, the question of what d is going to relate to the original equation involving d. So to find out what d is, we simply need to use Pythagoras, which is to say 3,000 squared plus 4,000 squared equals d squared. So what? This is going to be 9 million plus 16 million equals d squared. So that means 25 million equals d squared. And if you take the square root of both sides, you'll see that 5,000 is d. So Pythagoras gives us our d. Our d was the only thing left that we needed in order that dd over dt is the only unknown in our equation, and now we simply need to crunch the numbers. So 2 times 3,000 is 6,000. 6,000 times 600 is 36,000 times 100. 36,000 with 2 zeros. Okay, cool, that's that number. And then that's going to be equal to 10,000 times dd over dt. So to get dd over dt by itself, we just need to divide by 10,000. And then when we do here, the zeros are going to cancel out. I believe I've canceled out one too many. Okay, but the long story short is this expression is going to simplify to be 360. But now, 360 watts. Because if you're talking about a change in distance with respect to time, that's only relevant. Is it 360 inches per hour or feet per day, or what are the units? Well, what is the distance unit? The distance unit we've been using throughout has been feet, so since we measured 3,000 and 4,000 in terms of feet, the d is also going to come out in feet. And then, what is the time unit? Because we've also taken a derivative here with respect to time, so we're going to have a time unit in the denominator. And if you look throughout, the time unit is seconds, right? Because we dealt with 600 feet per second. So since the dx dt was in 600 feet per second, the dd dt is also going to be in terms of feet per second. And the long story short is the distance between the person and the airplane is changing at 360 feet per second. So interestingly, in spite of the fact that the plane is moving horizontally at 600 feet per second, the actual diagonal distance between them is changing merely at a speed of 360 feet per second.